The first stage of the Apollo 11 Saturn V, designated S1C6 for the sixth flight stage, arrived at the Kennedy Space Center on February 20th, 1969. Because of their large size, Saturn V stages were shipped to the Kennedy Space Center by ocean-going vessels and specially designed aircraft. The Saturn V was the first large vehicle in the U.S. space program to be conceived and designed for a specific purpose, that of landing a man on the moon and returning him safely to Earth. The birth of the Saturn V can be dated to January 10, 1962, when NASA formally announced development of the big booster. The 300,000-pound first stage is 33 feet in diameter and 138 feet long. At liftoff, it held nearly 4.5 million pounds of propellant, consisting of RP-1, a form of kerosene for fuel, and liquid oxygen as oxidizer. The first stage generated a total thrust of around 7.5 million pounds, operating for just 2.5 minutes to lift the vehicle to an altitude of about 38 miles at burnout. The awesome power of the Saturn V first stage was generated by 5 F1 engines. Each F1 engine was a single-start, 1.5 million pound fixed thrust engine. All of the engines were identical with one exception. The outer 4 swiveled or gimbaled for steering control. The center engine was fixed. The expense of the Saturn V makes it imperative that no effort be spared to assure that it will perform as expected in flight. The magnitude of the Saturn V ground test program was unprecedented. To qualify for flight, all components and systems had to meet standards deliberately set much higher than actually required. The inspection to which flight hardware was subjected was thorough. X-rays were used to inspect fusion welds, 100 castings and 5,000 transistors and diodes. A quarter mile of welding and 5 miles of tubing were inspected with the use of ultrasonics. The same type of inspection was given to adhesive bonds, which are equivalent in area to an acre. An electrical current inspection method was used on 6 miles of tubing, and dye-penetrant tests were run on 2.5 miles of welding. Each contractor had its own test program that was patterned to a basic conservative approach. Qualification testing of parts, subassemblies, and assemblies was performed to assure that they are capable of meeting flight requirements. Reliability analysis was conducted to determine the range of failures or margins of error in each component. A battleship test stage constructed more solidly than a flight stage was used to prove major design parameters. The stage verified propellant loading, tank and feed operation, and engine firing techniques. Battleship testing was followed by all systems testing. Finished work undergoes functional checkout to ensure it meets requirements. Fluid-carrying components are subjected to pressures beyond normal operating requirements. Rocket engines were static-fired before delivery to the stage contractor, and each stage underwent testing leading to a full-power captive acceptance firing. After refurbishment and a post-firing checkout, it was shipped to Kennedy Space Center. Upon arriving and being offloaded at the dock, the stage would enter a low bay of the VAB, or Vehicle Assembly Building. The VAB consists of a high bay area 525 feet tall, a low bay area 210 feet tall, and a 4-story launch control center connected to the high bay by an enclosed bridge. There are 4 assembly and checkout bays in the high bay area. The low bay contained 8 stage preparation and checkout cells equipped with systems that simulated stage interfaces. Saturn V stages went into the VAB low bay area where preparation and checkout began. After being towed into the high bay area and positioned under the 250-ton overhead crane, slings were attached to the first stage and attached to the crane. The stage is lifted to a vertical orientation and then positioned over the mobile launcher. At this stage in the process, the first stage is still missing the engine nozzle extensions and fairings and fins. These will be added later. The VAB had 141 different lifting devices at the time of the Saturn V, ranging from 1-ton mechanical hoists to two 250-ton high bay bridge cranes. Each pair of high bays shares a bridge crane. The cranes have a lifting range of 456 feet and a travel distance of 431 feet. When the stage is positioned over the mobile launcher, it is lowered into place. Then it is secured to 4 hold-down and support arms. These support the entire space vehicle during launch preparation and provide hold-down during thrust buildup prior to launch. The second stage for the Apollo 11 Saturn V S-26 arrived at Kennedy Space Center on February 9, 1969. On the Saturn V, the second stage employed cryogenic propellants of liquid hydrogen and liquid oxygen. For the lunar mission, the second stage takes over from the first stage at an altitude of about 38 miles and boosts its payload of the Saturn V third stage and the Apollo spacecraft to approximately 114 miles. When its 5 J2 engines ignite, the stage is pushing more than 1 million pounds. Speed of the stage ranges from 6,000 miles per hour to 15,300 miles per hour. The beginning of the second stage boost is a two-step process. When all the F1 engines of the first stage have cut off, the first stage separates. Ullage rocket motors around the base of the second stage then fire for approximately 4 seconds to give positive acceleration to the stage prior to engine ignition. About 30 seconds after the first stage separation, the part of the second stage structure on which the Ullage rockets are located, the aft interstage, is separated by firing explosive charges. This second separation is a precise maneuver. The 18-foot high interstage must slip past the engines without touching them. With the stages traveling at great speed, the interstage must clear the engines by only a little more than 3 feet. The second stage burns for about 6 minutes, pushing its payload into space. The 81-foot second stage is basically a container for its 942,000 pounds of propellant, with engines attached at the bottom. Propellants represent more than 90% of the stage's flight weight. The stage is constructed mostly of lightweight aluminum alloys ribbed in such a fashion that it is rigid enough to endure the pressures to which it is subjected. Special lightweight insulation had to be developed to keep its cryogenic propellants from warming. The second stage developed its power through 5 Rocketdyne J2 engines, a high-performance upper stage propulsion system. Each engine developed a maximum vacuum thrust of 225,000 pounds. All J2 engines were identical when delivered. They all were designed to be restarted in flight. The restart capability is only used in the third stage. As in the first stage, the outer 4 engines in the second stage gimbal, while the center engine is fixed. The second stage of the Apollo 11 Saturn V was erected at the top of the first stage on March 4, 1969. Using the 250-ton bridge crane, the stage was lifted into position with the aft interstage attached. The Apollo 11 Saturn V's third stage was moved into the VAB for checkout on January 21, 1969. The Saturn V third stage was an oxygen-hydrogen stage derived from the S4 stage originally created as part of the Saturn I program. The S4B stage was also used as the second stage for the Saturn 1B. The third stage had a maximum thrust on one J2 engine of 225,000 pounds. The stage was used for the final Earth orbital insertion and reignited to place the Apollo spacecraft on a translunar trajectory. The stage burned for about 2 3/4 minutes for orbital insertion and about 5.5 minutes for translunar injection.
Ignition.
We confirm ignition and the thrust is go.
Guidance looking good. Velocity 26,000 feet per second. Cut off. We're showing velocity 35,570 feet per second, altitude 177 nautical miles.
Apollo 11, this is Houston. We show cutoff and we copy the numbers and now 62. Apollo 11, Houston, do you read? Apollo 11, this is Houston. Do you read, over?
Roger, Houston, Apollo 11. We're reading the VI of 35579er, and the EMS was plus 3.3, over.
Roger, plus 3.3 on the EMS.
Because the stage was a part of the vehicle for an extended period of time, it contained an auxiliary propulsion module for attitude control. 2 APS modules were mounted 180 degrees apart on the aft skirt assembly. Each module contained 3 150-pound thrust engines and 1 70-pound thrust ullage motor. The Apollo 11 third stage, with its aft interstage, was placed above Stage 2 on March 5, 19. The instrument unit is the Saturn V's nerve center. It contains the electronic and electrical equipment needed for guidance, tracking, and communications of vehicle environmental and performance data. The IU also contains environmental control equipment for temperature control, batteries, and power supplies to furnish operating power for electronic equipment. The stage structure is 260 inches in diameter and 36 inches high and becomes a load-bearing part of the vehicle. It supports the components within the IU and the weight of the spacecraft. Several tracking systems are used to follow vehicle trajectory during ascent and orbit. Vehicle antennas and transponders, which increase ground-based tracking systems' range and accuracy, make up the IU's tracking equipment. The Saturn V is equipped with lots of equipment designed to detect malfunctions. Some of this equipment checks engine thrust and monitors guidance computer status, attitude rates, angle of attack, and abort request. This emergency detection information is flashed to the IU where it is routed to the emergency detection distributor in the electrical system. In the case of an emergency, the system will turn on a light in front of the astronauts. If the spacecraft abort selector switch is in the automatic abort position, the abort will take place without further crew participation. The action cannot be vetoed by the astronauts. However, if the selector switch is in the manual position, the crew makes the decision when to abort a mission.